multiply the 7. Add to 8.
These 7.
Yes. I did the same thing, except I had -5 divided by -1, and then I put 1 instead of 5. That's what I mean, like the hurrying through it. Because if you did this right now, it's negative. So if you take out the -16.
Well, be careful. When
The also take the negative 6 now. Because we're in negative.
negative point.
We need a negative here and a negative here. See this? We take the negative.
Point 1 is negative. Alright guys, we are going to get into chapter 7 now. Yes. Oh my God. As we continue our breakneck pace. 7 is all about radical expressions. And what does that mean? What does the word radical mean? In English, it has definitely a different connotation, right? What's it mean with mathematics? Yeah, like roots. So, a square root is an interesting little thing. What's the square root of 9? 3. But, how many answers does this equation have? How many things can I square and get 9? 2 things. 3 and negative. So when you see the square root symbol, it's what's called the principal root, the positive root. If I wanted the negative root of 9, I'd have to actually put a negative sign to tell people I want the negative root. You guys kind of give it. This has got 2 answers, plus or minus 3. When you see the square root symbol, it means the positive answer. That's why, of course, we know that square roots can never equal a negative number, right? Are we? Okay, good.
The number inside the symbol cannot be negative, right?
True, and stay real. Of course, at the end of this chapter, we're going to talk about the numbers that are not. Okay. So that's one thing to realize right there. Right. So if I say, what's the square root of 25? You guys tell me 5. What about negative square root of negative 25?
0.
It's not 0. Then you're telling me there's an answer.
Empty answer.
Not real. And you could say that technically you could say undefined because we haven't defined it yet in this class. So I know what you mean, but really just to hammer home the point, it's not real. There is an answer. It's just not a real number.
It's imaginary.
Exactly. Which is an unfortunate choice of words because students then say, well, there's evidence that math people just make shit up to make our lives more difficult. This is imaginary. I'm going to tell you that right off the bat. This is imaginary.
Can I put
That's when we start
5?
using that little eye.
Can I put 5?
No, you cannot because it's not right. These negatives, can they cancel each other?
No.
That can't hop inside of a square root, right? You can't just move stuff in and out of a square root sign. Cool?
Why not?
Because I said so. But what's this, of course?
-5.
Negative 5. We're all on the same page. So that's the real basics of square roots. Why do we call it a square root?
Because it's perfect square.
Yeah.
It's related to squaring, right? So what's kind of missing from this symbol then, considering how do I write the symbol for the cube root? A little 3 in here, right?
Yep.
Yeah.
So for some people, you got to be a little careful. It looks like you're dividing by 3 maybe, but I try to make sure that that's in the little spot for it, right? This is called the index of the radical, and this is called the radicand, and who cares? I don't care too much about names, just can you do the process? What's missing from this symbol then, really?
The 2.
A 2. It's not a 1 in there, it would be a 2. We don't write the 2 to save time. We say the square root is the most used root. If I don't put a number, everybody knows there should be a 2 there. It's an understood 2.
Yes.
Sort of like the billion understood 1s there are. There's a 1 there, there's a 1 there, there's a 1 there. Holy shit, and we understand those are all there, right? So what's the cube root of 8? Let's start off nice.
2.
Yeah, we know a lot of these cube roots from doing difference in sum of cubes. It's what you would get when you split the bad boy up into 3 parts. So a square builds things up. A square root cuts them down. All roots, all powers build things up. All roots cut them back down. That's why I end up with a smaller number. The cube root of 8 is 2 because it takes 3 2's to multiply to be 8. Cool. So that's the hard thing about roots. Roots are a little easier than some other functions we're going to learn later because we're more used to them. But you think backwards when you have a root. You think, what did it take this many of to make this? That's what you think. So what about the cube root of -27?
Not real.
Not the way.
Oh, jump the gun too quickly.
Oh, because it's 3 times.
Negative
So
3, negative 3.
Square roots, in fact, all even roots are very uptight. They can't handle negatives. Because if I have 2 of any number, it's always going to come out positive, right? 2 5s is positive, 2 negative 5s is positive. But what's 3 negative 3s? Negative 3 times negative 3 is 9, times another negative 3 is -27. So odd roots are laid back, like whatever. They can handle negatives. Because any odd number of negatives, if they multiply, there's still a negative left, alive. Any even number of negatives, all the negatives cancel each other out. Okay, cool. So what about, let's see, this guy. The 4th root. I'm not going to make it too freaky. 16.
2.
Careful. Square root of 16 is 4 because it takes 2 4s to make 16. It takes 4 2s. So if you have any trouble with this, one thing you can do for yourself is start breaking it up because that's what the 4th root wants to do. So 16 is 4 times 4, which is 2 times 2 times 2 times 2. So here's another thing you're going to hear me say a lot in this chapter. A 4th root, or any root really, but specifically a 4th root is looking for groups of 4 things. In 16, there's a group of 4 2's. That's why the 4th root of 16 is 2. Right? That also explains why, can you do this problem here? Because 8 is only made up of 3 2's. And a 4th root needs at least 4 of something in it, right? Because see, there's a lot of different ways to look at roots that make sense, and hopefully.
So not real for that then? Not real?
No, it's not real. It's sort of like the square root of 7. It's not. I like it. So here's another example of my English. It's not real. It's just ugly. It's just irrational.
Right.
So this is just irrational. It would be some ugly internal decimal, right? Okay.
Maybe I got irrational.
Well, if you hit a problem like this that says simplify, you said already simplified. That's all you have to say. You can't do anything with that, right? Okay. Let's see. Oh, what about this? Just to, where am I at in my Roman numerals here? Okay.
Oh, really simple.
Square root of 25 over 144. 5 5 over 12. I always get somebody do this though. Somebody always does that. If that were true, it's like, when would it stop? Square root it, okay, square root it, okay, square root it, okay, holy shit, when do you stop? Right, the square root of 25 is 5, the square root of 140 is 12. You don't need the symbol anymore, it did its job, let it go. Cool? Because that gets really freaky when you leave that radical and you're like, I'm not done yet, what happened? What about this? This is related to something somebody was just asking me earlier. Careful. We've lost a little bit of touch with what decimals do when you multiply. Yeah, it's 0.2. What's 0.2 times 0.2? 4. Remember what you do? 1, 2, 1, 2 places, right? Times another 0.2. 8, 1, 2, 3 places. Right? Do you guys see that? When a decimal multiplies by another decimal, less than 1, right? It gets even smaller. Because what does a decimal really mean? A decimal means a percentage. So this is like 20% of 20% of 20%. That's a damn small percentage. It actually comes out to be 0.8%. Right? So that gets a little freaky, but there are actually a couple like these in the earlier factoring sections. That's exactly, this is how you look at it. So if I had, for example, if I had x cubed minus 0.008, this is x, this is 0.2, 0.2, 0.2.
So it'd be negative 0.2.
So it'd be x minus 0.2, x squared, plus 0.2, x plus 0.04. Right, build it up the same way you would before. Okay, but there's a problem exactly like that one in the homework somewhere. Okay, how are we doing so far? I think normally you come in kind of knowing a little bit about radicals. I always feel like I'm teaching a political science course or something. The radical elements. Let's see, blah, blah, blah. Oh, what does a square root function look like? You're like, it looks like that, Jeff. No, I mean if you graphed it. Can somebody tell me, if I go to make a table of values, is that what you should always do when you hit a function you don't know what it looks like? You should make a table of values. What is the smallest number I can plug into my table of values? 1, 0. You're going to wait until you get a reaction from me. 0. Because you definitely can't plug negative numbers in there. But you can't plug a 0 because what's the square root of 0? 0, because it takes 2 zeros to multiply to be 0. Right? So when I plug a 0 in, I get a 0 out. When I plug a 1 in, I get a 1 out. Now I don't want to plug a 2 in. I'll get an answer, but it's ugly. What's the next smart number to plug in, of course? 4. When I plug a 4 in, I get a 2 out. When I plug out, what's the next one? Good one. 9. I get a 3 out. So blah, blah, blah. That's enough to graph this bad boy, right? It's not going to exist back here because you can't throw negative stuff in. So it's going to start 0, 0. Blah, blah, blah. Okay. So it's 0, 0, and then 1, 1. You might think, oh, no, but then it comes to 4, 2 suddenly. And then it becomes 9, 3. So see what it's doing? Now that's not asymptotic. That will go forever up. It just goes really freaking slow. Right? It's going to infinity. It'll just take it a long time. Well, it takes it as long as anybody else, but you can see it's growing very, very slowly. But anytime you think, oh, that's the ceiling, well, then you can just keep going and eventually it's going to pass it. There is no ceiling. It's going to go to infinity. How are we doing so far? So that's what any radical function kind of looks like. Any even root really is going to look like this. You guys do this. Try to graph this one. You see what you guys think about this. Think about what the smallest number is you could put in there, and then think about what are smart numbers to put in there. Let me see if you guys can do this. Of course, I'm waiting to see who brings out the graphic out. Don't do that. Do it by hand. Put it over here. Let me try to catch up to you a little bit. Who's got the smallest number you could safely put in there and stay real?
-3.
-3. 1 is a good choice for later, but as long as the inside is what?
0 or
Zero.
0 or bigger. So as long as the inside is bigger than or equal to 0. You guys remember how to find the domain for this case? You say in English what the restriction is. The inside's got to be at least 0. Write it in Mathish and solve. There you go. It's got to be at least -3. Because -3 makes it 0. That's the smallest number I can take the square root of. So square root of 0 is 0. What's the next good number to have inside? 1. What does x have to be to make it 1 inside? You guys see how to look at this kind of problem. If I make it -2, I get the square root of 1, which is 1. The next good thing to have in there is 4.
So 1.
Make x 1,
1.
and you get square root of 4 is 2.
6.
6.
Yeah, 6 would make the inside 9, which make the output 3. You can keep going, but that's good enough. You guys see how you have to think about what's a smart thing to plug in. Don't just plug numbers in willy-nilly, you get these freaky ass decimals. I'd rather graph whole numbers. Stay with me. Holy crap, and a half. All right. That's terrible. So -3, 0. Now, why do you think I'm allowed now to be on this side? We couldn't go on that side over here, because you can't have negative inputs for the square root. But when x is negative, that some of them let the inside still be non-negative, right? The fact that I'm adding 3 to everything I plug in lets my inputs be 3 smaller than they could be before. So do you see how the whole picture is just going to move back 3? So at -2 we got 1. At 1 we get 2. And at 6 we get 3. Make all my points big. It's the same as that, it's just picked up and moved back 3. You guys see that? So if I said x plus 5, it would have just gone back to 5, and then had the same picture. X minus 2 would have gone the other way, and been the same picture. Yeah?
What is it, if you put x as 3, that's just not being smart because then the line goes
It
down.
would still come out with a number, but it would be an ugly number. Square root of 6 is not a nice number to find on a graph. You can still do it, but it's better to get those nice integer numbers that are easier to graph. Yeah.
So the best way to do it is to make it equal 0. Make the
To start with.
To start
exactly.
with,
That's
right.
where your starting point is, and then you go from there.
Okay.
You think about what would make the inside become a number I could do the square root of. So what would make it 1? -2. What would make it 4? 1. You know, that's what you think about. What would make it come out to be something I can do easily?
Okay.
Okay. You can do all the same things you've done before with graphing. I mean, I could give you a line coming and say, what's the solution, and you just find out where they intersect. The same way we did before. The graph calculator doesn't care what kind of function it is. You can find the intersection of any two functions no matter what they are. Right? As long as there is a place that they meet. Okay. So let's get to the freaky stuff. For example, and I love it, you're all like, what? This is freaky. What's the square root of x squared? No. Ha. It's getting closer. Still not quite right. I like it. Square root cannot come out negative. If x, for example, if x is negative 2, I get this, don't I? But what's negative 2 squared? And what's the square root of 4?
2.
Not negative 2. So it can't equal x. There's no way, because then you'd say that if x is negative 2, then the square root of something is negative. No, we know that can't be. So how do you force? What's the easiest way to force the answer to be always positive?
Absolute value.
Absolute value. Or, at least 0. Right. So technically, when you do that, one level I want you to realize, and most of you guys got this, the square root and the square, they just cancel. The absolute value is just to cover my ass in case x is negative, right? So what about this here? What if I had the cube root of x cubed?
Absolute value of x?
Nope.
No.
X.
X.
I like that. It's like I set you up for that. I'm sorry. But remember, cube roots are cool with negatives, aren't they? Cube root can come out negative. So for example, if x is negative 3, this is like the one we did earlier. What's the cube root of negative 3 cubed? That's negative 27. That is negative 3. So if x is negative 3, the answer is negative 3. So that cube root of x cubed is x. So which roots are the uptight ones that need help with negatives?
Even.
The even roots. The square roots, the fourth roots, the 80th roots. Any even root cannot handle negative inputs, can't give you negative outputs, right? So they have all this weird stuff going on. Odd roots are cool with negatives. Nothing freaky happens there, whatever you want, right? So let me ask you this. We looked over there, sort of at the domain of something. How would you figure out the domain of this? Already did an example up here. X plus 1 is at least 0, right? Can't be less than 0, must be greater than or equal to 0. If you solve that, now, I could have been evil, but I wasn't. I could have been evil, and I could have given you this question first. That's the easy question. You're like, well, that would have been evil. Yes, it would have been evil, because you guys would have done the work we did, which wouldn't have been right. Does a cube root have any restrictions on the inside? What did you just say? Cube roots can handle negatives, right? So what's the domain of that one? Everything, all real numbers. It has no problems, right? Notice how do you see now why we're so careful about saying all real numbers when we say domain? Because we don't know yet what the complex numbers might do to it, because we haven't looked at them yet. Are you guys kind of with me here? That's another example of why even roots have all this extra little stuff associated with them. Odd roots don't. They're cool. They can take it.
So for function of x, I was writing something. That's the answer. X is.
Yeah, this would be the
greater than
domain for that function,
domain.
right? So, or you could write it, of course, like
Right.
this one would be all real numbers. Yeah. Okay. So you'll see a couple of domain questions in this section. Just make sure first what kind of root it is. If it's a 7th root, all real numbers, no problem, right? Any odd root has no problems. Let's take the next step up. So you guys can take this next step. This shouldn't be too evil. What's the 5th root of x to the 10th? What do you think? What's your gut tell you that should be?
All real numbers?
No, not the domain.
Oh.
What is the 5th root of x to the 10th?
X squared.
X squared.
Square.
Because what does it take 5 of to multiply to be x10? It takes 5x squares, doesn't it? So look at this beautiful shortcut. 5 goes into 10 twice. Now watch, somebody else will say, well, what about the cube root of 27? There's no 3 goes into 27. That would be wrong. I agree. 10 is not a number. It's an exponent. It will act differently than a pure number would. This is not 3 goes into 27. What is the answer for us? It's 3. Now, if I write 27 as a number to a power, what would that look like? And 3 goes into 3 once. And that's the answer. So if it's written as a power form, the shortcut is take the root, divide it into the power. That's freaking awesome. Have you noticed why on this one I didn't really care about putting the absolute values? Can x squared be negative? Can x squared be negative?
No.
Considering we haven't gotten to the imaginary number section yet? If you square any real number, can it be negative? If you think so, give me the example, please. No. If you square any real number, it's going to come out at least 0, if not positive. You cannot square a real number and have it come out negative. Impossible. That's why I didn't have the absolute values. It's already positive. If you put them there, fine. Right, like that. It's better than never putting it there. But okay, how are we doing so far?
Can you do another example for the one?
I don't mean to ignore you guys, but there's so many freaking people. You're looking that way, and I'm like, what? All right, it's like the gravitational pull in my eyes. All right, let's see. There's just so much stuff related to this. I want to give it to you now. We've already done that. Already done that. Blah, blah, blah. Okay, just try a few of these out here. Oh yeah, that's funny. And technically there should be an absolute value there, but you'll notice something in the homework. They very quickly go away from that. They very quickly say this. Assume that no radicands were formed by raising negative quantities to even power. Basically saying assume that you don't need freaking absolute values. Assume that x can only be positive. Because the absolute value thing, even when you have a problem where it might be needed, you use it when it's obvious you need it. What I really care about is that you know how to handle this kind of problem, period. What about the cube root of 64x cubed y 6? And you do it just like you do any algebra problem like this. You take the numbers and then you take the letters as they come. So the cube root of 64, we've seen that with cubes in factoring, right? 64 is 444, so that's 4. 3 goes into 3 once. 3 goes into 6 twice. And you can check yourself by multiplying this by itself. You know, 3 of them. Right. And then you should get this. That's how you can check yourself on these. Okay.
What section are you in right now?
This is section 7.1, by the way. We've gotten into chapter 7 now. Oh, let's see. They don't really throw too much at you in this section, thankfully. There really isn't that much in here. That's awesome. Yeah, it's great. So that's fine. One last thing from this section, I think. You'll notice how they are not going to let you get away from functions. Every section there's a function piece, which is good. You got to reinforce the idea of functions. So what do you do? How do you solve it?
Plug it in.
Yeah, plug a 30 in. 4 times 30 is 125, right? Add the 5 in there, of course. What's the cube root of 125? 5. This is another one you really should have picked up when we were doing that difference for sum of cubes. That 125 should have shown up a few times. Okay. Yeah.
For the 16x squared, why wouldn't you put an absolute value of your answer?
I said you would normally, but this actually came out of a section where they say assume that the variables do not represent negative. So they want you to get away from worrying about when to use it, when not to use it, and just get to the idea of how to work the problem out. All right. Okay. That's really all there is in this first section. It's kind of nice. So most of that, huh? No, one more section. What time is it? Yeah, one more. Cool. Let's see. Yeah, cool. So one last section, then we'll head out. Yeah, cool. That shouldn't be too bad. The first section really should not be that bad.
7-2.
7-2. Here's where we get to the what I think is a really interesting part about this. Radicals are definitely directly related to powers, right? We saw that because the cube root of x cubed, they cancel each other out. In fact, a power, if I take 2 and raise it to the third power, the third power makes there be 3 of them, right?
Yeah.
If I take 8 and cube root it, it undoes that. It says, it took 3 2's to make this 8, so the answer would go back to 2. So this 3 up here, it's 3 2's multiplicatively, right? Now, when I talked about cubes, difference of cubes, sum of cubes, I said we break everything up into 3 parts, didn't I? That doesn't mean 8 divided by 3. It means 8 broken up multiplicatively. That's why it makes sense that a cube root can be written as a 1/3 power. Because it's 1/3 of this thing multiplicatively. And where do I put numbers that relate multiplicatively? We put them up in the power. Powers are based on multiplication. Let's investigate this. Cube root of 8, let's just look at that a little bit closer. I can write 8 as 2 to the third power. Now, we say these cancel, and of course they do. The cube root is the opposite, the inverse of a cube power, right? So they cancel. But what would I raise this 2 to make that 3 cancel to 1? What do I have to put here? 1/3. Because wouldn't that multiply and those 3's would cancel? So there's a kind of a, not a proof, but the cube root does kill that 3, and how would it look then as a power? It'd have to be a 1/3 power. So let me show you kind of a cool way to look at this. If I write 8 to the 1/3 power, it's really saying break 8 into 3 parts and take one of them. That's what that really says. So 8, of course, is 2, 2, 2, and that says take one of them, so 8 to the 1/3 is 2. Because you can rewrite that if you wanted to as the cube root of 8. Notice that roots go on the bottom, like they're in the bottom of plants. My botanists out there, leave me alone about the roots that are on top. I know there have been, most plants have roots on the bottom, right? So the bottom is the root, the top is the power. So if I had, for example, 8 to the 2/3, doing it this way is nice. Break 8 up into 3 parts and take 2 of them. So this answer should come out to be 4. But let's see how to write it differently in case you don't really like that way. And I don't want you to do it that way every time because it's going to get ugly that way. Well, how do I rewrite 8 to the 2/3 as a root? What's the root? 3. It's a cube root of 8 to the second power. Roots are on the bottom, powers on the top. How we doing? And just to kind of check this real quick, what is the cube root of 8? That'd be 8 to the 1/3. And what would you do with those? Multiply? Isn't that the same thing? Right? Maybe some kids would. So roots are on the bottom, powers on the top. Cube root of 8 is 2. 2 squared is 4. The same thing we got doing it the other way. So that's kind of cool. Now we got a more complete sense of what powers really mean, because we haven't been able to do fractional powers yet. Now we know what the hell they mean. So what about this? Which part do you think you should do first? Which part's kind of the ugliest part of that? That you're like, why did you have to make it that?
The negative.
Negative, okay. So do that first. What will that negative do? Be careful, it does not make it 4/3. You cannot tell me that negative 3/4 equals 4/3. That's neat. What is that negative power acting on? What's it acting on? What's being raised to a negative power? 16. That's what should flip then, right? I always get somebody tell me that this is 16 to the 4/3, which is basically impossible to do by hand, right? You can't flip itself. A negative power makes the thing flip. So this will become like this. Now how do you rewrite that power? What's the root the power is trying to tell me? What's the root? Fourth root of 16 to the third power. And what's the fourth root of 16? 2, because it takes 4 2's to multiply to 16, right? That's the process you go through to evaluate a radical. What does it take this many of to make this? So 2 cubed, 1/8. Yes, ma'am.
Is there such thing as negative root?
Oh, no, not really. I mean,
Like
on the fringes of math, you got people playing around with shit, but we're never going to see like a negative third root of something. That gets exceptionally difficult to define, right? Because a square root, like a fourth root, means what does it take 4 of to make this? A negative fourth root would be trying to say, what does it take negative 4 of to, and you're like, what the hell does that mean? So that gets a little freaky. So we're not going to get anywhere near that. All of our roots are going to be at least 2. 2, 3, 4, nice whole numbers, right? Is there such a thing as a first root? If you had a first root, like a first root of 11, it's 11.
Yeah.
What does it take a 1 of to make 11? So of course we don't have, that's silly. We'd have no first roots. So here, you guys try this one. What's Jeff? I don't know. Yeah. It's just a suggestion, but I think it helps out a lot if you take care of that negative first, and then just rewrite the bottom as you go. So the very first thing is to flip the whole thing over. What root are you trying to take?
3.
Third root. Roots are on the bottom. To the
4th power.
4th power. Cube root of 27 is 3 to the 4th, and you can just do that and you calculate whatever that's.
8.
Funny thing about 3 to the 4th, 3 squared is what? 3 squared? 9. So 3 to the 4th is 3 squared, 3 squared. 9 times 9 is 81. Right? So you can build it up a little bit quicker that way. Okay, last problem, then I'll let you guys have it.
Wow.
Really, you just go, aw. I
I
like
said
it.
wow.
Oh, wow. I was excited for a second. Aw.
I wouldn't do that.
Well, let me make it start.
They might do that.
Just get straight to the point here. Yeah, cool.
How much do you hate us again? A lot.
Remember that properties can never change. Just the stuff that I'm throwing into the properties change. So properties never change, ever. What do I want to do with these exponents then? Add them, because I'm multiplying like bases, I add the powers. I don't care what the hell they are. In fact, I had m's up here at one point, remember? What the hell's m? Whatever the hell it wants to be. So if it's fractions, I don't care. You do the same stupid thing. You want to take 4/5 minus 1/10, right? Not a bad idea to rewrite it so you can focus your attention on this. Beautiful. Don't forget you need LCD. You don't only need an LCD when it's a fractions only section. Wherever the hell their fractions trying to subtract or add, you gotta get LCD. So you get 8/10 minus 1/10. Got it. Divided by a to the 7/20. So are you cool with me so far? Right, you gotta make that into, let me do it here, 8/10. Now they're like denominators, 8 minus 1, 7/10. What do you do with these?
Minus.
Subtract.
Subtract, sorry.
So when you divide like bases, you subtract the powers, right? So it'll be 8 to the 7/10 minus 7/20. LCD is easy. Yeah. So 14 minus 7, 7/20. Bam. Right? Nothing new to learn there at all. Nothing new at all there. We already know the properties. We already know how to combine fractions. Nothing new at all. Like whatever you say. That's plenty. That's good. So tomorrow I was considering, and you guys, I already know your answer to this, but I was considering, instead of doing the quiz, doing like a little group exercise at the beginning, right, over those sections. Maybe even, well, everybody's in a different place in homework, but we'll do a little group exercise at the beginning. Then we'll do some graph and calculator work. We'll get a few more sections into 7. Wherever we get to is where the test will go to, right? I'll have the...
Thursday. Or Wednesday, yeah.
Tomorrow, yeah.
Oh,
Yeah.
That's Wednesday.
What is today?
Wednesday.
Thank you. Yeah, so tomorrow is the last day for new stuff before the review on the 5th and the test is on the 6th.
Is this all of 7-2 that we just did, or is that just partial?
It's all at 7-2, yeah, basically. I mean, there's a couple little specific things, but we'll do some of those next time.
Tomorrow we still have a quiz, right? Tomorrow we
So tomorrow, what does that mean about tomorrow? Do we have a quiz?
No, no.
No. I just said we're going to replace that with some group work. Yeah. So we'll let everybody else sweat it out.
Ready to quit? Yeah, I can just get it done. We're done.
Chapter 6, we're going to have some group work tomorrow. Oh. If you're behind, yeah, well, thank you.